Okay, Bismillah ar-Rahman ar-Rahim. Let's continue our discussion on the transformer production. So we have discussed that earlier that we can use the circulating current protection. Okay, and in that circulating current differential protection, two problems are faced. The first problem, that is the problem of the spill current, and this spill current that flows through the relay because of the non-identical saturation characteristics. And the second reason is the unequal lead length. Okay, so we have discussed these 2 points in the earlier classes. Okay, so the one is the spill current. The spill current is due to the non-identical CT saturation characteristics, and the second one is the unequal lead length. Okay, so because of these 2 points, two problems, the differential current that flows through the relay. Okay, and the relay maloperate if we go for circulating current differential scheme. So the remedy is to use the biased or percentage differential protection scheme. So this is our today's topic. So in earlier case, circulating current differential protection scheme, the relay, this is the relay, right? It has only one coil. Okay, this is the relay, which is only one coil. Okay, as you can see in the figure, that is known as the operating coil. Okay, this is the operating coil, and the I1 minus I2 are the differential current. Okay, this is I1, this is I2. So I1 minus I2 is the differential current flow through this relay. Okay, now is the biased or percentage differential protection scheme, the another coil that is known as the restraining coil is also connected. Okay, so where is the restraining coil? This is the restraining coil. Okay, this is also connected at the midpoint of the restraining coil. So the current here, that is I2, and this current, that is I1. So the current through this operating coil still remains I1 minus I2, right? If I take absolute value, and if for the restraining coil has n number of turns, then the current flow for half, okay, half of the turns, that is I1, and another current that flows through half of the turns of the restraining coil, that is I2. Okay, so n are the number of turns. This is I1, this is I2. So n1 flows through half of the turns, and 2 flow the remaining half of the turn. Okay, so taking common n, I1 plus I2 divided by whole 2. Okay, so this is the current through the restraining coil. So again, the value will be I1 plus I2 by divided by 2. Okay, this is the net current. Okay, so the current that flows through the restraining coil, that is the average restraining current. If the average current, that is the I1 plus I2 divided by 2. So if we use this, then because of this two problem, non-identical saturation, CT saturation characteristics, and unequal lead length, I2 and I1, even through they are not equal, and still an unequal, and still spill current flows, then also this relay has two setting. Okay, so let's discuss the setting. The first setting is known as the busy setting or the sensitive setting. Okay, sorry, the basic or the sensitive setting. and the second one is the bias setting. So the basic setting or the sensitive setting that is given by I1 minus I2. So this is this is the current that flows through the operating coil of the relay. Okay, so I1 minus I2. This is the current that is flowing through the operating coil of the relay. Okay, that is the bias differential relay. So this is the first setting of the relay. That is the sensitive setting or the basic setting, right? The second type of the setting that is known as the bias setting. Sometimes this is also known as percentage bias, or sometimes it is also known as the slope setting. Okay, so the slope, this is the slope setting. Okay, so the slope setting is given by the ratio of I1 minus I2 divided by I1 plus I2 whole divided by 2. Okay, this is the formula. Percentage bias due to I1 minus I2 divided by I1 plus I2 whole divided by 2 multiplied by 100. Percentage bias. So this you will get in percentage. So you can see that if in case of circulating current differential protection, the spill current I1 minus I2 flows because of two problems as we have discussed. In the case of bias differential relay, even though differential current is there, the spill current uh, is there, and this setting exceeds, but the percentage bias setting, this is not going to exceed, because even though I1 minus I2, that is spill current flows, the denominator value, okay, this is the denominator value. The denominator value, you have the average restraining coil, the restraining coil current. This will also increases. Okay, in case of this, so the percentage bias will reduce. Okay, so that means if I consider the bias setting, then using this setting, whatever is the problem, okay, whatever is the problem of okay, whatever is the problem faced by circulating current differential relay because of the non-identical CT saturation characteristics and unequal lead length, or because of the flow of the spill current, this type of problem that can be avoided if I use bias uh, or percentage protection scheme. Okay, so now let us discuss that the characteristics or bias differential relay. So the characteristics of this relay that is given or plotted, consider on y-axis, we can consider the differential current, that is I1 minus I2, and on the x-axis the bias current, that is I1 plus I2 divided by 2. Okay, the differential current I1 minus I2 on the y-axis in per unit values, and through the bias current I1 plus I2 whole divided by 2, these on the x-axis. Okay, so you can see that the characteristics is like this. So any portion above this characteristics, that is the operating region. Okay, above this operating region, and the portion below this curve is the non-operating region, or you can say that the blocking region. Okay, now when we consider any point, for example, the differential current Okay, now if we consider any point, right, say the differential current flows or the spell current flows through the relay because of two reasons, then that point, because of the increase in this value restraining current, that will again come or fall down somewhere here. Look, this is the value. Okay, this value is the restraining current, and this will again come fall down. Okay, so now it is always in the blocking region or the non-operating region, so the relay will not operate at all. Okay, and the mal-operation of the relay, that can be avoided. So before we apply this biased differential relay or any type of differential protection scheme to the transformer or the power transformer we are talking about, in this case the power transformer, then few points we need to consider. Okay, these are the few points. So let's see what are these points. This first point, that is the line charging transformer primary rating. Now we know that the transformer voltage and the current rating, that is entirely different. So if I consider LV side and HV side, the current are entirely different. So whatever CT we use, then in that case the CT ratio is also different. Why CT ratios are different? Because suppose, for example, if I consider 220 kV by 132 kV delta star transformer, then the MVA rating is 100. Okay, then the current on 220 kV side and 132 kV side are different. Okay, okay, this is the example I've discussed. This is the CT ratio. Okay, this is the 220 side of the transformer and 220 kV, and this is the 132 kV secondary side. The delta one is 220 kV and the star is 132 kV. Okay, so the CT chosen will have the ratio of 300 oblique 1 ampere and 400 oblique 1, 300 dash 1 and 450 dash 1 ampere for these two sides respectively. Okay, so these two are entirely different. So for example, for 220 kV, we have to consider CT ratio, that is 300 by 1 ampere, and the CT located on 220 kV side and the CT located on 132 kV side, the CT ratio I have considered is 450 by 1 ampere. Okay, so this is actually, I think it is 22 kV. Okay, so you can see the primary rating of both CT1 and CT2 on each side of the transformer, that is entirely different. However, the secondary rating, that is always same, which is 1 or 5 ampere. If the current is above 1000 ampere primary side, then the secondary rating, that is 5 ampere. If the primary current is less than 1000 ampere, then it is always 1 ampere. So that means the primary ratio is, let us say, 1000 by 1 ampere, then you always go for CT secondary, that is of 1 ampere. And if it is more than 1000, if it is more than 1000 by a 1 ampere ratio, then you will go for the 5 ampere CT secondary. So this is very important, and this point need to be considered when you consider or when you apply the differential protection scheme in case of the power transformer. Okay, so why this point is important? Because this primary rating that is different, even though secondaries are different, then uh, these two secondary currents are different, and when you apply these two currents to the relay, differential current that always flow through the relay. So this need to be take care when you apply the differential protection in case of the power transformer. Okay. Now the second point we need to consider is the no load current of the transformer. We know the transformer, the primary current of the transformer is given by IP primary current, that is equal IS times some transformation ratio K, and IS is the CT secondary side current plus I naught. So I naught is the no load current of the transformer that contains magnetizing component as well as some low loss component. Okay, so the no load current of the transformer, that is roughly 1% to 2% of the full load current of the transformer. And when you decide the setting of the relay, then the relay is capable to take care of this point, that is no load current of the transformer. Okay. Let us discuss the third point we need to consider when we apply the differential protection scheme for the power transformer. So the third point, that is known as the inherent phase shift, exists in the power transformer. Now, when we consider the delta star transformer, and we know that in actual substation practical field, whatever transformer we use, power transformer, that is either delta y one vector group, or it is either delta y one vector group. The other vector group dy7, dy5 are not used. So we use only either D1 or dy11. Okay. So here I have shown the diagram for the D1 vector group. This is the D1 vector group. Okay. dy1 vector. So this is the dy1 vector group delta star transformer with the connection 1. dy1. Okay. Now when we consider this, you can see that this current capital IR, this IR and the small current IR, small current, these two are equal. Okay, why? Why these two are equal? Because when you found the transformer, these two coils are again mounted on the same lane. So the capital IR and the small IR both are same. So if I draw the vector diagram, okay, this is the vector diagram, you can see this small IR, IY and IB, both all the three are at how much degree? 120 degree apart from each other. Okay, and that is the phase with the capital, and this is, and similar is the case with the phase difference of the capital IR, capital IY and capital IB. Okay. IR, okay, and this is small IR, capital IB, okay, this is capital IB, small IB, and capital I R, sorry, capital IY, small IY. Okay. Now taking the negative of each vector, this is capital IR, so this will be minus uh, capital IR for the parallelogram law. Okay, this is the capital I B, So minus capital IB, similarly capital IY small minus capital IY. Okay. So according to these vectors, you can see that IRL is will be equal to IR minus IB. IYL is equal to IY minus IR. IBL will be equal to IB minus IY. Okay, these are IRL, IBL, and IYL. Okay. Okay. However, if I just look at the current IRL, then this IRL is nothing but from this point. If you mirror it in IR minus, then the current available from B phase, that is IB. So this IRL is nothing but the IR minus IB. Okay. So if I draw a vector diagram for IRL, then it is IR minus IB. So your plus is IB is here. So minus will be over here. Okay. Okay. The secondary current IR always lead the primary current IRL by how much degree? 30 degree. Okay. This is the 30 degree. So that's why, or sometime it is also as, so this type of connection is known as 1 o'clock. Okay. If I consider dy11 vector group, then the phase shift available, that is how much? That is minus 30 degree, and the available point, that is somewhere like this, like 11 o'clock. Okay. So this is 11 o'clock. Okay. So why the connection name this, that is 1 1 or 1, and in this case the secondary current IR lags the primary current IRL by 30 degree. That is why the minus 30 degree connection or 11 o'clock connection is named to this connection. Okay. So whenever we give or whenever we apply a differential protection scheme as differential relay to the transformer, delta star transformer, then we have discussed that there is an inherent phase shift of 30 degree plus minus depending upon the vector group you use, either 1 or 1 1. Whenever we apply the differential current or CT secondary current from LV side and CT secondary current from HV to the relay, the differential current always flow through the operating coil. So this current, these two current given to the relay, that is equal in magnitude as well as as well as in phase, both in magnitude and in phase. Okay, differential current should be same both in magnitude as well as phase wise. So this is very important. Okay, differential current should be same in magnitude as well as the phase current. So we need to do some arrangement to compensate this phase shift, inherent phase shift that exists in the delta star transformer depending upon the vector group used, either dy1 or dy11. So how to avoid this? So to avoid this, what we do is the delta connected, that is the star connected. This is again the dy delta connection in this diagram. You can see this is the dy or the delta star connection. So the remedy to compensate the 30 degree phase shift whatever delta side of the winding, okay, the connection is there. Whatever CT I use here, that CT I connected in star, and the star side, at the star side, the star winding of the transformer, whatever CT I use, that I connected in the delta side. Okay. So delta side, whatever CTs are used, line CTs are connected in star, and on the star side, uh, the line CTs are connected in delta. Okay, these are the delta side, and these are the star side. Okay, and this is the connection of CTs on either side, delta side and Y side. Okay, so keep in mind this delta should be okay. Okay, keep in mind this delta should be same as your dy1, okay, as shown in the figure. So if you connect like this, then whatever phase shift is there, that can be avoided. And whatever current you can see, the primary current is IRL, IYL, and IBL on delta side. On the secondary side, 180-degree out of phase shift. That is IRL and IBL. Okay, IRL, IYL, IBL, and IRL small. Okay, IYL small, and BL small. Okay, this current should be equal to this current given on this side, that is capital IR, IY, and IB. So small IR, IY, and IB, these two currents, these currents should be same. Okay, and this current should be same, and the other side, this current should also be same. Okay, these current must should also be same, and these current should also be same. So the current on these three current are equal in magnitude as well as in phase, because this is the relay which has biased differential relay, which has 3 operating coils and 3 restraining coil, one for each phase. Okay, so this means if we go for any compensation, then we have to connect the line cities like this, as we have shown in the figure. Moreover, if we connect like this, then this is also going to eliminate the zero sequence current on the star side, while the zero sequence component on the delta, that is not produced outside the delta, it remains circulated inside the delta. On the other hand, if I use the star star connection, then the cities on both sides, that should be connected in delta. But however, star star connected vector group, normally we are not using, we use either d1 or dy1 or dy11. Okay, so now the next point is the we need to consider, that is a bias to cover the tap changing facility. We know that most of the power transformers are inherently contain the tap changing facility. Okay, so tap changing transformer are widely used, and hence cities that can be chosen based on which tap, highest tap, nominal tap, or the lowest tap. So normally when we decide CT ratio, we decide the CT ratio based on nominal or the fixed tap. That is normally the central tap. Okay, the central tap. Okay, the nominal tap. So the transformer operating for any type other than the nominal type or the central tap. That means if we decide the CT ratio based on nominal tap, and then if I change uh, the tap and put or use the highest tap, then in that case, because of the mismatch, some current that will always flow through the relay. So this current need to be compensated, and this is known as again the spill current. Okay. Okay, so the mismatch of the current that will over and above the mismatch because of the non-standard CT ratio or unequal lead length. So the unbalanced current that may be sufficient to cause the relay operation. So in practice, there are two options. What is the remedy of this? The remedy is we can go for either bias differential and the bias differential relay. Even though we use bias differential relay, then this relay setting are decided on the nominal tap. So if we consider, we have to consider the worst case, and then we decide the setting, particularly the bias setting of the differential relay. But however, we decide the setting based on the worst case, then for some conditions, the sensitivity or the operation of the relay that is affected, it reduces the sensitivity of the system. So the best option is to you need to go for the adaptive setting. Okay, the best is the adaptive setting. So we know that ideally the differential current through should be zero. However, it is not zero because of the reason I have explained you, because of the taping. Okay, so this situation is more crucial. Now, if we consider the difference in the mismatch, that is the lower than the bias, whatever percentage uh, of the bias setting or the slope setting, that can be easily take care of this. Okay, but if the difference in the current because of the tap change in the tap, either the highest tap or the lowest tap, this difference is high, very high, then the bias is not capable to take care of this. So in that case, we need to change the bias, percentage bias adaptive, based on the change in the changing in the typing of the transformer. So this is known as adaptive setting. Okay, so sometime it may be possible that whenever we use delta star transformer, then as I told you that the delta side we have to connect the line cities in star, and star side we have to connect the line cities in delta. Okay, means star side we have to, star side of the transfer we have to connect the city in the delta connection, and on that delta connection side of the transformer we have to connect cities in the star connection. Okay, so that the 30-degree phase shift can be easily compensated. However, sometime in actual field they do not connect both sides, delta side star city and star side delta city, they connect both sides star star. So in that case, you have to use the other option that is known as the interposing current mismatch of the transformer. So interposing current transformer are again the non-standard cities, and these cities are at the low voltage. That means if I wish to compensate the magnitude of the current as well as phase shift at lower voltage, lower current, then we can go for the interposing current transformers. So in this case, when we use the interposing current transformer, it can easily compensate whatever is the mismatch in the magnitude as well as in the phase. So this type of cities are always connected on the secondary side of the original or the actual current transformer. So on the secondary of the CT, you connect one more transformer, that is the CT, and this is going to compensate the magnitude as well as the phase of the differential relay, so that the current is fed in each of the differential relay that is equal in magnitude as well as in phase. Now, the next phenomena is that is known as the magnetizing inrush current. Okay, so magnetizing inrush is a condition when the transformer draws a very large current from the supply while the load current is either zero or of nominal magnitude. This means when you energize the unloaded or lightly loaded power transformer, then the transformer draws a very high magnitude of the current. That current is known as inrush current. Keep in mind, this inrush current is not uh, okay, this is not the fault current. This inrush current. Now, however, whenever the draws, this inrush current is not the fault current. However, whenever the draws, the current inrush current, its magnitude is maybe from 5 to 10 times of the full load current of the transformer. So whatever relay we connect, it treats such type of phenomena as a fault, but actually uh, it is not a fault because it is going to die down once the normal condition is established. Okay, now to understand this phenomena, let us consider the voltage waveform between the voltage and the flux with the reference to time and the phase difference between these two, that is theta. Let us assume now when the flux that is going to establish inside the core of the transformer, when you uh, when when you energize the unloaded or lightly loaded transformer, then this flux can be asymmetrical or symmetrical in nature. So whether the flux that is going to establish in the core of the transformer, that is symmetrical or asymmetrical in nature, that depend on the reaching instant of the voltage signal. That means whatever this voltage, uh, okay, this voltage, this is the V voltage and this is the flux. So whatever this voltage signal I have shown, at what instance the transformer that is going to decide whether the flux is going to established in the core of the transformer is symmetrical or asymmetrical. If the switching of the transformer is carried out when the voltage wave is passing through its peak value, uh, here its peak value, then the flux, this is the peak value, okay, then the flux that is going to establish in the core of the transformer, that is symmetrical in nature and is given by the phi, that is phi maximum plus, okay, phi maximum plus minus phi r, where phi maximum is the maximum value of steady state flux that is going to establish in the core of the transformer, and phi r, that is nothing but the residual flux in the core of the transformer. So in this situation, what will happen, as the flux is symmetrical in nature, so BH curve or whatever point that always operates in the linear region of the BH curve, and hence the magnitude of inrush that is restricted to a small value. Okay, okay, now uh, Okay, the core of the transformer that is directly proportional to the current. So the magnetizing inrush result in a large flux value and flux density in the core of the transformer. At this point of the time, the core volume of the transformer that remains minimal. So whenever transformers are designed to operate, they have to design in such a way that it always operate below the knee point of the curve. Okay, so if point x is the value, okay, if point x is the value, the transformer enters the saturation region, and that is not in the linear region of the BH curve, but it is in the non-linear region of BH curve. Now, conversely, if the switching of the transformer is done when the supply voltage is passing through its zero value, then whatever flux that is going to establish, that is asymmetrical in nature, and that is given by again the same equation, but the tube that comes in picture in the previous picture. So in this case, the upper point of the BH curve that gets in elongated, it does not remain in the linear region of the BH curve, and hence in order to produce the same amount of the flux, the magnitude of the current that produces the voltage. So the magnitude of the current that becomes very high. So the magnitude of the current becomes very high. Okay. During magnetizing inrush, a large flux results in saturation of the transformer. Thus, the flux waveform will be asymmetrical with respect to the time axis and will contain a DC value. The nature and the magnitude of the inrush current will be decided by the direction and magnitude of the residual magnetization flux in the core and switching instant. Okay, so that was all for the today, and in the next class we will discuss a numerical based on the transformer protection, differential transformer protection. Okay, so that's all for the moment. Thank you.